Have you ever stopped to think about the invisible forces all around us? You know, the ones that let a massive steel ship float or make a baseball curve? Well, it all boils down to the physics of fluids. And today, we're going to break it all down, uncovering the simple rules that explain everything, from the pressure inside a water bottle to the incredible power that lifts a 747 into the sky. Let's dive in. But first, I've got a question for you. A 10-Newton force, that's about the effort it takes to lift a quart of milk. So how on earth can that tiny little push lift a 5,000-kilogram car? I know, it sounds completely impossible, like some kind of magic trick. But I promise you, by the end of this, you'll see it's pure physics. So here's our game plan. First, we're going to set some ground rules by talking about something called an ideal fluid. Then we'll get to the star of the show, pressure. After that, we'll see how to harness that pressure to do amazing things. And finally, we'll look at what happens when fluids start moving, which is where the real magic happens. Okay, so before we can understand the really cool stuff, we have to set some ground rules. In physics, we often start with a simplified model to get a handle on the big ideas. So we're going to begin by defining an ideal fluid. Think of it as our perfect theoretical liquid that helps us see the core principles without any messy, real-world complications getting in the way. Our ideal fluid has three basic rules. First, it's isotropic, which just means its properties are the same no matter which direction you look. Second, it's homogeneous. Its density is perfectly uniform all the way through, no lumps or clumps. And third, it's non-viscous. That means it has zero internal friction. Its layers slide past each other perfectly, kind of like a puck gliding on an air hockey table. All right, it's time to meet the main character of our story, at least for the first half, pressure. When you're talking about fluids that are just sitting still, pressure is everything. It's this constant, invisible force that a fluid is always exerting, pushing on any surface it comes into contact with. Now, the most important thing to get about pressure is right here in the definition. It's a perpendicular force. That means it always pushes straight into a surface, never at an angle. And the amount of pressure is just how much of that straight-on force is being applied over a specific area. And this formula right here is the golden rule for pressure in a stationary fluid. It's actually pretty intuitive if you think about it. Imagine you're diving into a swimming pool. The deeper you go, the more water there is stacked on top of you, right? Well, all that water has weight and it's pushing down. This equation just tells us that the pressure you feel at any depth is simply the pressure at the surface plus the weight of all the fluid above you. It's why deep-sea submarines have to be built like absolute tanks. And here's the flip side of that coin. If you just move sideways through the water without going deeper or shallower, the pressure stays exactly the same. This sounds super simple, right? But believe it or not, this one little rule is the secret sauce behind some seriously powerful technology. Okay, so we've got our basic rules for pressure down. Now for the fun part. Let's see how we can use these simple ideas to build machines that literally multiply force. It's time to go back and solve that puzzle from the beginning. And here it is, the solution to our mystery, the hydraulic press. Take a look. On one side, you've got a piston with a really small area, and that's where we apply our tiny little force. On the other side, you've got a massive piston with a huge area, and that's what's lifting the car. The secret is the fluid connecting them. And here's why it works. Remember our rule? At the same depth, pressure is the same. So, when we push down on that small piston, we create a certain amount of pressure in the fluid. That pressure gets transmitted equally everywhere throughout the fluid. So that same pressure is now pushing up on that huge piston. And because pressure is force divided by area, the same pressure acting on a much larger area produces a much, much larger force. It's a force multiplier. Now, pressure doesn't just let us lift cars. It also creates another amazing effect: buoyancy. Think about it. The deeper you go, the higher the pressure. So for any object in water, the pressure pushing up on its bottom is always a little bit greater than the pressure pushing down on its top. This difference creates a net upward force. And that upward force is what we call the buoyant force. So why do some things float and other things sink? Well, it's a battle. You've got gravity trying to pull the object down, and you have the buoyant force pushing it up. If an object's average density is more than the fluid it's in, gravity wins, and it sinks. But if its average density is less than the fluid's, the buoyant force wins, and it floats. That's exactly how a submarine works. It lets water into its tanks to get heavier and sink, and pushes the water out to get lighter and rise. So far, we've only talked about fluids that are sitting still. But things get really wild when fluids start to flow. We're now leaving the world of hydrostatics and entering the much more exciting world of hydrodynamics.
The first big rule for moving fluids is called the equation of continuity. And honestly, it's something you already know instinctively. It just says that for a fluid like water, what flows in one end of a pipe must flow out the other. So if that pipe gets narrower, the water has to speed up to get the same amount through that smaller space. You've done this 1,000 times with a garden hose. Put your thumb over the end, you shrink the area, and the water jets out way faster.
And now for the main event, Bernoulli's principle. And yeah, I know, that equation on the screen looks a little intimidating, but don't worry. All it's really saying is that for a moving fluid, its energy is constant. It's just a trade-off between its pressure, its potential energy from its height, and its kinetic energy from its speed. If one of those things goes up, another one has to come down to keep the total amount of energy the same. The easiest way to think about this is like an energy budget. A little packet of fluid has a total amount of energy it can spend. It can spend it on pressure, on height, or on speed. If it decides to speed up, its kinetic energy increases. Well, that energy has to come from somewhere, so its pressure might have to drop to balance the books. This trade-off is the absolute key to understanding flight. We've built up all the concepts we need. Now for the grand finale. Let's use Bernoulli's principle to explain one of the greatest marvels of modern engineering, how a gigantic metal airplane can actually get off the ground.
So if we just ignore big changes in height for a moment and focus on that energy trade-off, Bernoulli's principle gives us this one incredibly powerful takeaway. When a fluid's speed goes up, its pressure goes down. And when its speed goes down, its pressure goes up. Faster flow equals lower pressure. That's the secret. Burn that into your brain.
Okay, look at an airplane wing. It's a masterpiece of engineering. The top surface is curved, so the air flowing over it has to travel a longer distance to get to the back. The bottom surface is flatter, so the air there travels a shorter path. This means the air on top has to move faster than the air on the bottom. And what did we just learn? Faster air means lower pressure. And that's the aha moment. You have low pressure air above the wing, and you have higher pressure air below the wing. The higher pressure underneath pushes up harder than the lower pressure on top pushes down. The result is a net upward force. And that force, my friends, is lift. It's what pushes a 400-ton jumbo jet into the sky. So let's do a super quick recap. We learned that for stationary fluids, pressure gets bigger the deeper you go. And we saw how that lets us multiply force with a hydraulic lift. Then for moving fluids, we found out that if you squeeze them through a smaller area, they speed up. And the big one, when fluids speed up, their pressure drops. Those 4 simple ideas explain so much of the world around us. So, from lifting a car with just a little push to launching a massive plane into the air, the rules of fluid mechanics are just incredibly elegant and powerful. And they're everywhere. It really makes you wonder, doesn't it? If a few simple principles of physics can explain something as complex as flight, what other mysteries of our universe are just waiting for us to uncover?